gonna go around the other day and one that too.
All right, everybody, I'm gonna go ahead and get started here. Welcome to week 5 already of the semester. Boy, where is the time going? So it's so fast already, I think. I hope that you guys had a good weekend and that busy things to keep us going. It's true for me too. Trust me, my bedtime is getting later and later. I know I'm in trouble when the custodians show up before I leave. Hasn't happened yet, but it could happen before the semester's over. It wouldn't be the first time. Anyway, yeah, it's a busy time, and I do appreciate all your hard work. You know, I just wanted to say, so I graded the quizzes. They were a mixed bag. There were some very high scores. I don't actually think anybody quite got 100% on it, but I know there was at least one or two 19.5s. But then there was also a whole spectrum going down the pike a ways. So what that means is that, you know, we're all kind of in a different place with trying to understand these counting problems. And, you know, that's even true for me. I have to say that, you know, it's a blessing and a curse that in this type of subject, you don't have a lot of formulas. You don't have sort of a progression of definition, theorem, corollary, and all the sort of what you would think of as a more mechanical process of going through, say, theorems in a real analysis class or something like that. This is sort of more of a grab ideas out of the sky in different places that make sense. And you don't need a lot of prerequisites to do that sometimes, which is nice in a way, but it's also challenging in a way because it means that, yeah, I don't quite know exactly where to look to solve this problem. So if I could give you anything to sort of try to go back to, and this does not work as a perfect diagram all the time, and we've talked about this, but there's two important questions that we can be asking ourselves, which is, you know, so I'll put the questions over here. Does order matter? And on that penguins problem, the order basically did not matter at all because we were not putting the penguins in a particular arrangement. We were just choosing. We were always just choosing them. And then the other question is repetition allowed? And on that one, on the penguins problem, I think I had a couple of parts of the quiz where it said, assume that all the penguins of the same species are identical, meaning you can repeat the same penguin multiple times. And then I had a couple other parts where it said, all of the penguins are considered distinct. And if they're all distinct, then the repetition is not allowed. So what I wanted to do with this little space here is kind of create a little 4x4 grid. So let's suppose, sorry, figure out how I actually want to draw my picture. So we could have, you know, the answer to question 1 is yes, or the answer to question 1 is no. And then we could have 2 is yes, or 2 is no, right? And they're kind of independent of each other. And then we can make this little table. And what I'm going to encourage you to do is think of a familiar problem that you've seen that would fit these descriptions. So if the answer to both of these questions is yes, order does matter and repetition is allowed, think of some example that you've seen that reflects that. So one example would be license plates, right? As you have the order that the characters are in the license plate does matter, but you can see license plates that have the same character multiple times, right? But you may, over the course of time, add other things to your list, like the students choosing faculty advisors, right? So which student chose which advisor, that matters. So the order matters, and the same students can choose an advisor more than once. Repetition is allowed. So you might think that of that as also fitting into this category, and that's fine. So you're going to see other problems where these sorts of things are allowed. Or you have the fire trucks that are all identical, right? And they're being assigned to a fire. So you can repeat the same fire for 21 different trucks if you wanted to, right? So feel free to take this diagram that I'm drawing and add more things into it, but I'm gonna give you kind of what I think of as like the first example or the prototype of an example for each category. Let's see, what if the order does not matter, but yes, repetition is allowed? This would be the example of buying fruit at a grocery store. Doesn't matter what order you pick up the apples, the oranges, and the bananas in. That does not matter. But you're allowed to pick up several apples, several bananas, several oranges. So that's kind of a good example to model that type of a problem. What else? What about over here? What if order does matter, but the repetition is not allowed? So that's going to be a permutation with factorials. Because as you are not allowed to repeat things, then the number of choices in the slots goes down as you go along. This could be photographs. So, you know, something like that might work. Photographs are a good example of that. And then what about if the order doesn't matter, but you're not allowed to repeat anything? That would be poker hands with the deck of cards, right? That's a great example of that scenario. Assuming that you only have one deck of cards, if you suddenly decide to shuffle multiple decks of cards together, well, then you're starting to allow repetition of the same type of card multiple times. But I like to sort of have these 4 primary examples in mind, not that it always is a perfect fit, that the problem that you see perfectly matches this. But for example, when it says something like, all of the penguins are distinct, and I have to grab exactly 5 penguins from each species. Penguins being distinct would mean repetition is not allowed. Order matters, that's a no, right? So I come over here and say, oh, that's like poker hands. And with poker hands, of course, we have spades, clubs, hearts, and diamonds. With penguins, we have chin straps, emperors, Gen2s, whatever, whatever they were, Magellanic and Rockhopper, whatever they are. But you're choosing out of each of those piles, you're going to choose 5 chin straps, 5 Rockhoppers, 5 Gen2s, and so on. And so it's very similar to if I had said how many poker hands can you make that have exactly 3 of each suit? 3 hearts, 3 spades, 3 clubs, 3 diamonds. You probably could all do that. It's 13 choose 3 times 13 choose 3 times 13 choose 3 times 13 choose 3. You just grab 3 from each suit, and that's 13 choose 3 raised to the power of 4. If you make that analogy, then you can realize, oh, well, with penguins, it's the same idea, except I have 30 of each of the types of penguins rather than 13 cards from each suit. So the 13 has to be changed to 30. And I'm choosing 5 of each penguin, not 3. So it's going to be 30 choose 5 to the 5th power. So you can kind of get to the answer that way by sort of relating the problem to another problem that's similar to that. And then hopefully you're in a more comfortable situation here. Like, yeah, I've done problems before. Well, like the one that said, I want to have at least 3 chin strap penguins. That's like the poker hand that I have to have at least 1 club, right? And the way we actually did that one in class. We said, oh, well, we have all possible choices, 52 choose 5, and we subtract those poker hands that have no clubs. So we subtract the violations. It's exactly what I had in mind for this problem, the last problem on the quiz as well. So overall, the first page was really good for the most part. I mean, not perfect, obviously, but it's pretty good overall, I would say. Few people need to maybe look at it a little bit more, but the second problem kind of got people, I think, by the time, well, not that it was that bad, but there's a few people had trouble with some of the later parts of that. So the solutions, I emailed them out to you guys. Definitely keep those around and review this again. You know, I don't know if this is a good exercise or not, but you could actually try to see if you could write a quiz that is like a mirror of my quiz. And, you know, just grab a partner that you might want to try this with, and you could each try to write such a quiz. So you have to change the penguins to something else, right? And slightly, so we've done, I did fire trucks on the group work, then we did penguins, and you've seen other examples. See if you can write your own fairy tale story of these types of problems and make a little set of questions about it. And then have a partner do the same thing, and then like give each other's quiz and see if you can talk through. I could see that being a valuable exercise. Because yeah, this stuff, like I said, it is kind of hard to teach this stuff just because it doesn't just fit into a nice theorem, equation definition type of format. And so it takes maybe a little bit of a unique approach to studying, I think. I wanted to also mention that we have our first midterm 2 weeks from today. So it's on October 8th, it's Tuesday. In Canvas, I am going to be putting together a review packet. I know you're working on some homework right now. There will be one more assignment that you'll have after the current one you're working on. The next one, I think, is just one section of problems, pretty short. In the meantime, I'm going to be assembling a folder into Canvas that's going to have some stuff for the midterm. I'm going to put a sample exam in there, a sample midterm, which I don't think you should start with. I think you should study a little bit first, right? And maybe start by studying the group works again. Or even maybe some of the homeworks if there were some sections that bothered you a little bit. But I'm also going to have a review packet that's going to have a whole nother slew of sample problems. I really do believe that this class requires a lot of like just hammering the practice problems as many times as you can to see these different examples. It's one of the reasons I wanted to get on the quiz, was to just give you another exposure to sort of these types of problems. But there's going to be a bunch more of that in this review packet. And then, like I said, once you've studied a little bit and you feel like you're kind of feeling decent about the material, then I'll probably suggest that you try that sample test. Give yourself an hour and 20 minutes or something to try that sample test. And that should help you to get ready. I'm also thinking about doing a review session for the exam. Now, I know finding time that everybody's available to come do a review. I won't be doing it during class. But what I might do is set up a time outside of class to do it. And I would record it, of course, in Zoom. And I would also allow you to attend in Zoom so that if you were interested in it, but you couldn't come to campus, because this would probably happen on somewhere around on a weekend, or not on a Tuesday or Thursday for sure, because I'm way too busy teaching Tuesdays and Thursdays. I haven't really picked a date yet for that, but just keep that in mind that that'll probably be coming once I get this packet together. I'll figure out a day and a time to do that. For this week though, just a normal week, we have a homework assignment. It was originally going to be due on Tuesday, but then I looked at the problems towards the end of the homework that's due in the current assignment. And I realized we probably should practice a little more first and give you guys a couple more chances to catch me. I did send you a note yesterday, though, about what's going on this week for me. On Thursday, I'm going to be collecting a massive truckload of exam papers. How many different orders can I put those in? Don't get me started. I'm going to have a lot of grading to do, and I really want to get on top of it. So on Thursday, my plan is to try to do my office hours from 5:30 to 7, but then probably take off for the night a little early so I can get a jump on that other work, so I'm not like ruining my entire weekend over it. But that's kind of what I'm thinking. So just keep that in mind a little bit. I do have office hours today, so right after class all the way until 10 o'clock with a dinner break in the middle of that. I'll mostly be around. I'm actually going to be around tomorrow as well. That's because, well, my other class has an exam. So I told them I would hang out tomorrow. You guys are welcome to crash in on that too. I will probably try to prioritize. I mean, I love you guys more, of course, but I might prioritize the other students just this once, since they do have a test on Thursday. They're all freaking out. Trust me. They're like, I've got them so scared of everything right now. I don't know what's going to happen. So I'm going to try to help them out tomorrow and get them ready for their exam on Thursday. But anyway, so any questions about like I said, there's an assignment this Thursday. There'll be another assignment due next Thursday. So I'll give you a whole week to do that assignment, and then you'll have that following weekend. We'll probably do review session. You'll have that resources folder to just dive into, do the practice problems and all that. And I think that should be relatively spaced out for good pacing for you. I hope so anyway. So that's my plan. Okay, and what the exam will cover, by the way, it will cover everything we're covering in class up through chapter 6. We're still in chapter 5, actually. We're going to finish that today with these combinatorial proofs. And then chapter 6 is about the inclusion-exclusion principle. And I'll be discussing that starting on Thursday probably, and then a little bit next week as well. So that's kind of where we're at. Just trying to keep on pace here, which I think we are so far. Okay, so on Thursday last week, what we started doing was this idea of writing up a combinatorial proof. This is where you can prove an equation not by crunching some formulas or using algebra, but instead by counting something in two different ways. Where in one way, it's obvious that it adds up to whatever's on one side of the equation. And then in the other way, it's obvious that it adds up to whatever's on the other side of the equation. But since you were counting the same thing, those two totals that you've accrued have to agree, right? They have to be the same amount. And so that's actually how you end up proving the equation. Like something like this maybe we'll start with this as a warm-up today. For all m greater than or equal to 2, let's prove that m squared is 2 times m choose 2 plus m choose 1. This could be proven just using the direct formulas for the binomial coefficients. M choose 2 has a formula, m choose 1 is just m, and you could literally just clean this thing up and you'd see that it works. But I would actually like to try to prove it using a combinatorial proof. So I'd like to think of something that I could count, that I could do it in two different ways. And I'm wondering if there are any thoughts about that here. Do you have an idea, Fernando?
Yeah, I do. I'm thinking like since we have like m squared on the left side, you have like m times m. It's kind of like when you have like strings of size 2, and you have like m choices for each like box.
Yeah, you kind of think, well, where would an m squared come up in a counting problem? It's exactly the right way to think about it in my perspective. It's like you have two slots and you have m choices for both slots, right? The number of ways of creating a two-string or a string of length 2 using m different options for both slots is just m squared. So how about license plates of length 2? Where we have an alphabet of m letters available to us, something like that. So let's do that. So for the solution, consider license plates. And I haven't even thought about the right-hand side yet. So I'll have to come back to that. But for right now, consider license plates of length 2 with m available letters per slot. So you have 2 slots and you have m letters available. So your alphabet has exactly m things in it. So then by the multiplication principle, by m period p, by the multiplication principle, there are m squared such plates possible. Right? So you have 2 slots here, m choices, m choices. So here we've created a physical problem, something that we can count in a physical way. And I've given you one way of thinking about it. Now, here's where the real thinking comes in, though, is that I have to figure out how to arrive at the right-hand side is supposed to be this counting the same thing. Is there a way of explaining how these 2 slot license plates would add up to this many things here? Yeah, Julie, you have an idea?
Is there two options? One option is that they're different letters and the other option is that they're the same letter.
I like it. So we have a plus sign here, which makes it sound like two cases being added together. How could we have two cases if we're talking about license plates with two slots? Well, it could be that as Julie said, it could be that the same letter appears in both slots. Or it could be that it's two different letters, right? So let's break that down according to the numbers we see on the right-hand side. You see how that's gonna work, right? So let's just say such plates could consist of the same letter twice. Now, if we were creating a plate like that, my question is, how many such plates would there be that have the same letter in both slots? Choose one, right? I just choose the one letter, I put it in both slots, right? So there are choose one such plates. Exactly. So such plates could have the same letter twice, or I mean, we could actually list this as maybe a case 1 and a case 2. Sorry, I should have tried to break it into cases to begin with. I sort of said it, but I didn't write it very well. So here's case 2. The plate has two different letters. Now, if my plate has two different letters, do we?
It can be in their order.
They could be in either order, which is where the 2 is coming from. And what's the choose to?
The two letters that you're just.
Choosing the 2 letters. So I'm choosing the 2 letters without putting them in order. And then I have 2 choices to actually then put them in order, right? Does that make some sense? Right? So there's choose 2 ways to choose the letters. And then 2 ways to order them. Right. That's kind of the idea. That's kind of the idea. So then by the multiplication principle within this case, sorry, I'm going to write on the very bottom line here, guys. Sorry about this. It's a little bit low. Feel free to stand up if you can't quite see it. This case has 2 times choose 2 plates. Okay, and then so finally, the last thing is, all right, so then we have to use the addition principle. Okay, so adding the 2 cases yields 2 times choose 2 plus the choose 1. And so thus, we have, and I do like to have a final conclusion sentence here. We have m squared equals choose 1. Sorry, I'll write it the way it was written just above it here. 2 times choose 2 plus choose 1. And that would be the end of the proof. Okay, so that's the idea of a combinatorial proof. Questions on that? Now let's try another one then. If that one's good, I'm going to do a couple more of these. Some of these get a little more interesting as we go along. They get to a point where you can't always just do it an algebraic way. This one you probably could as well. We'll call this number 2. Let's try a second example of this. Let's try to prove that for m greater than or equal to 3 this time. So I'm going to give you a slightly different one. If I take 3m choose 3, it's equal to 3 times m choose 3 plus 6 times m choose 2 plus m cubed. Slightly bigger example that we could have here. Okay, so again, the left side is very simple. It's just 3M, choose 3. That sounds like not putting anything in order, but I'm choosing 3 objects from 3M objects, and somehow the 3M objects have to be kind of somehow organized well. So trying to think here, what could we maybe set up for a scenario? The challenge of this, maybe also the fun part of this, is to think of what is it that we could try to count, that we could do it in 2 different ways. I'm wondering, Nikolai, do you have a thought?
Maybe like fruits or something,
One more time?
maybe fruits.
Fruits. So maybe we have M apples and M oranges and M bananas, and we just want to choose three of them. Right? And these would have to be like, they would all be distinct objects, right? So exactly. So let's run with that idea. It's not what's in my notes. I had M red balls, M blue balls, and M green balls. And I basically said, how many ways are there to choose 3 balls? Right. It's the same idea though, as what Nikolai suggested. So let's just to make my life more interesting. I'll go with that example. So let's do it. So consider choosing 3 pieces of fruit from among M apples, M oranges, and M bananas. My only complaint is I'm getting kind of hungry. I missed lunch today, so this is not gonna help. But that's okay. So the left-hand side is just how many ways are there to choose 3 pieces of fruit. Now, do you see why it is important here that the fruits are all distinct from each other? I don't just mean the apples are distinct from the oranges, which are distinct from the bananas. I literally mean that they need to be, the individual apples are distinct, and the individual bananas are distinct, and the individual oranges are distinct. Otherwise, I would just be choosing, 3 apples, or I'd be picking 2 apples and an orange, or 2 apples and a banana, and so on, and I'd only have a couple of ways of doing it, some small little number, and it wouldn't be 3M choose 3. I need to have 3M distinct objects. It's not just 3 distinct objects, right? So even though I've tried to distinguish apples, oranges, and bananas, within those categories, I have distinct objects as well. It's just like all penguins are distinct from each other. That includes the individual chinstrap penguins and the individual gentoo penguins and so on. So it's that kind of a setup here as well. Yes.
If we made this example or used the balls, would you want us to stay distinct?
Yeah, we would want to say that. So let's just add that, all of which are distinct. I think it's really helpful on these types of questions because it can be otherwise very easy to misinterpret it. Yeah, okay. So on the one hand, honestly, guys, this looks just more like an essay than anything else. Okay, it's not you're gonna hand this to your math friends and lower calculus courses and say that's from a math class. It doesn't look like it. It's like we wrote an essay, right? So on the one hand, there are 3M choose 3 ways to do this. We're choosing 3 pieces of fruit from among 3M distinct pieces of fruit. It would have been the same answer as if I had literally had only one of 3M different types of fruits. There's 1 apple, there's 1 orange, there's 1 banana, there's 1 strawberry, there's 1 peach, there's 1 kiwi, there's 1 watermelon, and so on, right? You'd have 3M of those, whatever number that is, and you choose 3 of them. It'd be the same exact answer, right? And that's because I'm viewing the apples, oranges, and bananas as all being distinct from one another. But the reason that I didn't just say
why don't we just take 3M distinct pieces of fruit, is I need to work now on the right-hand side. I need to think about cases. I see the plus signs again, which makes me think about cases. What kind of cases might we be breaking all of these outcomes down into? Can anybody tell me a case that might come up here?
Kind of like what you were just doing over there, like you'll have only apples. Or two of one fruit, one of another, or. one of
Okay,
each fruit.
yeah, exactly. So this is gonna depend on whether I've got, you know, just one type of fruit represented, or whether two of them are represented. Three of them are represented, right? So let's take a look at some cases here. We can consider these outcomes in cases. So first thing will be case one. And case one might be all fruits are of the same type. All fruits are the same type. So can somebody tell me how many ways would there be to grab 3 pieces of fruit if I'm going to require that they all have the same type? So they're all apples, or they're all bananas, or they're all oranges. What would be the answer here? 3. I have to take out of each. Well, I have 3 choices of which fruit I'm going to
You
repeat.
choose one.
And then out of that type that I've chosen, I have M of those fruits, I choose 3 of those. Right, that's basically the way to think about it. So this is from, let's just say, 3 choices for a fruit. And M choose 3 ways to choose them. And again, if the apples were all identical, and you said, I'm gonna choose 3 apples, well, there'd only be one way to do it. So that's why it's so important that all of these fruits are distinct, right? That's really key to making this work. Okay, great, so that's case 1. Case 2 is, what's case 2? Okay, 2 fruits are the same type, and then a third fruit that is different. So 2 fruits of the same type. And 1 other. Put a little colon here, and we'll just give a total on this piece as well. So how many ways are there to choose the 2 fruits that are going to be from the same type? 3M choose 2 puts all of the fruits together, and then I'm just choosing 2 of them. I don't get a guarantee that they're the same type though. So maybe we should choose the type first and then pick the fruits from within that type. That make sense? How many ways are there to choose a type of fruit here? 3. So there's 3 ways to choose a type of fruit, and then out of that type, we're gonna choose 2 of them, right? So we then multiply by 3, choose 2. So that maybe gets us, I don't know, 2 bananas. But then I need to pick 1 more fruit. So what else do I have to make for a choice?
Which one of the other two,
Which of the other 2 fruits it's going to be?
and then which. fruit
And then
within
which of those, let's say it's oranges,
So I'm
which
choosing
of those oranges you're going to get? Right? So we can write it like this, and I'm going to simplify it in a second. But yeah,
Would you also be able to do 2 M?
2.
Putting it all in one like basket?
Yeah, you could say, so these 2 combined together would be 2M, choose 1. You could say, yeah, of the other 2 types of fruits, just grab 1 of them. That's totally possible. Let me just write down an explanation here. There are 3 choices for repeated fruit. I'll say repeated. Then M choose 2 ways to pick those fruits. I'm gonna need more room. Let me come over here to continue this case two. Then two choices for a second type of fruit. And M choose one ways to choose one of them. It's a fair bit of writing, as you can see. That's case two. Obviously, we need to clean up this expression here, but I'll do that when I summarize the argument at the end. Finally, the last bit of this is case three. And this is where we are going to do what? What's the third case going to be? One of each kind, right, exactly. So one fruit of each type with M choose one ways to choose the specific fruit. And so that's for each of the three types. So this gives me M choose one actually is cubed when you do that. Okay, and so now again, we kind of get our rubber stamp together. We're going to add the cases. Adding these cases. What we have then is that 3M choose 3 is equal to, the first case was 3 times M choose 3. The second case, I'm going to simplify that answer now. It's just 6M times M choose 2. And then the third case is just M cubed. And so we're done with that proof. That kind of finishes that one off. Does that make sense? Okay, let's do one more. And then we're going to do some group work. You guys practice a little bit for yourself as well. Let's try one more, if everybody's okay with this. I also want to point out that, like, I'm not super fussy about the exact write-up. So as you can see, I chose a certain style of what I did. You might not put it exactly in these terms, or maybe you don't do the cases in the same order or something like that. That's also fine. Or your example could be different. I was like grading these because, like, oh, you know, one person does fruits, another person does colored balls. Somebody else might have a different example. You know, you could make up your own creative real world scenario. That can be kind of interesting. Let's do one more. Let's do one more of these, and then I'm going to feel better that we've had a good practice. Let's prove that. Oh, sorry. Let's prove it twice. No, for n greater than or equal to 2, n times n plus 1 times 2 to the power of n minus 2 is equal to the summation where k goes from 1 to n of k squared times n choose k. Okay. A bit more interesting. You know, and sometimes, you know, like on the first one we did over here, Fernando's idea of focusing on what would represent m squared made a lot of sense. That was actually the easier, simpler side of the equation. So sometimes that can work nicely, but there's also situations where, you know, it's actually the more complicated side of the equation that gets you a foothold on what kind of object you might want to be counting. Like the summation here on the right side to me is something that we could represent as like, oh, that's a bunch of cases that we're adding together. So it can be helpful to think on both sides of the equation, what would you be counting? This n+1 is really weird, by the way. I would have been more happy if it said n times n-1 times 2 to the n-2. I would have felt like that was like falling factorial or something, but this is weird, n+1 there, to me. So let's just think if we could think maybe a scenario on the right-hand side is a little more approachable. Fernando?
That's kind of like the one that we did with the committees, where like you have n choose k ways to make the committee of size k,
So you choose a committee,
and then.
that's n choose k,
Choose like president,
and then you choose a president,
but then you have another, let's say you have a secretary to choose from.
a secretary. That sounds pretty good to me.
Yeah, that's all I am.
I like it. So the size of the committee would be k, right? So you have n people in this room, right? We're gonna choose k of us to form a committee, and then we're gonna choose a president from there. So we have n choose k ways to actually make the committee first. Then we choose the president. There'd be k ways to do that, because that's how many people who are on the committee. And then you're choosing a secretary also. That's why it's k squared. But there is one weird thing about that, which is the same person could be this president and the secretary at the same time, right? Because it doesn't say k times k-1. That would have suggested that there was a secretary and then somebody else was the president, right? Where you're not allowing repetition. When I see the k squared, that reminds me that I'm allowing for repetition. But I actually like this idea. So let's focus on that. I have not even thought about the other side of the equation yet. So we'll come back to that. The first thing I want to do is just explain the right-hand side. So what we have is consider committees of size k chosen from n people. There are, we can go ahead and write down how many there are already. There are obviously just n choose k of these. So that's like the first task, is to just make the committee. Then secondly, I'm going to choose a president, right? So from the committee, there are k ways to choose a president and also k ways to choose a, did you say secretary? Secretary. Where the two officers could be the same person. Be a very strange way to do things, but we're, the example doesn't have to be, something that physically happens in reality. It just has to be something we count. So there are k squared times n choose k ways to construct this by the multiplication principle. By that multiplication principle, we then can sort of multiply that out, and this is what we would have. Is my handwriting okay? Readable? Okay. Then I just have to add up the cases for what k could be. The size of the committee can't be bigger than the total number of people that you have, but there better be at least one person there, because you are choosing a president and a treasurer. We could have a committee of size 1, and that person is the president and the treasurer. So summing over k from 1 to n gives, and now we write it down, the summation k from 1 to n of k squared times n choose k such committees. So that's kind of one way of expressing this, and now we're gonna, while I'm erasing, I want you guys to think about why the left-hand side could be counting exactly the same thing. Okay, so let me come back over here again, and we'll try it. So on the left-hand side, guys, we're not sort of focusing on what the size of the committee is. That was the K value that was on the right-hand side, and I don't see the K here. So the left-hand side, somehow, we're not worrying about that piece of it. Do you have an idea there?
Well, I was just thinking about like,
Okay, I'd love to hear it.
it kind of looks like, what is-
Well, it's a triangular number. It's actually, it would be n plus one choose two is what it would be, but it's weird because I don't have n plus one people. I only have n people to begin with, so how could I be choosing from n plus one? That's the weird part to me. Yeah, that's the part that I don't quite follow. I mean, couldn't we just say, well, how many committees would have the same president and secretary? And then how many committees would have different presidents and secretaries, and just add them together? I do see a plus sign on the left side. And basically separating two different terms. So we've created committees of size K that have, where K could be anything from 1 to N, where the president and secretary are allowed to be the same person. So maybe we could count how many of these committees would in fact have the same person, and then how many would not, and just see what that gives us. Do you have a comment?
A thought about the two amendments too.
Okay.
Uh,
Officers. Yeah.
and The rest of the people, we need to see if they are in it or not in it, so.
You kind of get that sense, don't you? Yeah, that's exactly my thought. The two, you have multiple powers of two here. That sounds like in or out, in or out. Each person in this room, you're either in the committee or you're out of the committee, right? But we're not doing 2 to the N, because after all, if we said everybody was out, then we wouldn't have a president or a secretary. So there's got to be at least a couple of officers, which could be the same person or could be the different people. So I think we're starting to get a game plan here, right? These committees kind of have two types. The first type is where the two officers are the same person. The second type is where they're different people. Once we've established those officers, we're going to say in or out for everybody else. Let's try and write it down. And I mean, we'll know the nice thing about these problems is, you know, if you've done it right, because you got to get the right answer, right? We know what we're supposed to get here. So, consider these committees in 2 cases. Right, so that's the way I think might be a fruitful approach here. The first case is the president and secretary are the same. We might have the same person. So let's think about our choices here. How many choices are there for who that president and secretary would be? N, right? So N choices for this officer position. It's actually a double position, both the president and the secretary, followed by. So once we've chosen that person, now everybody else in the room can either be added to the committee or left out of the committee. So followed by 2 to the power of n minus 1 choices for adding other committee members from the N-1, I'll call them non-officers. So the people who are not the chosen officer, there would be that many choices. And so by the multiplication principle, I know there's a lot of writing here, guys. Bear with me, my wrist is getting tired too. By the multiplication principle, we have, what would it be? N times 2 to the power of n-1 committees in this case. It's kind of weird because I don't see a 2 to the n-1 and I don't, yeah, it's not quite lining up right. So, well, I'm gonna hope that the second case is going to make this all work out. So we're gonna have a second case here. Is everybody comfortable so far? Really is like writing an essay. So the second case would be the president and secretary are different. The president and the secretary are different. So in this case, can somebody help me out with how the choices are gonna line up here? Go ahead, Abby.
Is it n times n-1?
Okay, so for just getting the officers, right, I'll have n choices for a president, and then if it's a different secretary, there'd only be n-1 choices, right? So let's just say n choices for the president. And then n-1 choices for the secretary. And after those two people have been chosen, what else do we have to do? Two choices for each other person, whether they are on the committee or not on the committee, right? 2 times 2 times 2 times 2, and there's n-2 other people. So 2 to the n-2 choices for adding other committee members. I'm not going to write the whole thing out again, because this is kind of a ditto of the first part. Okay, and so by the MP again, by the MP, we have n times n-1 times 2 to the power of n-2 in this case. And now I've got to add those together. Oh, I might just practically use the whole, almost more than half the room just to write this proof up. Yeah, so the only thing I have to do now is do the addition principle, right? So by the addition principle, I guess that's the AP. I don't know why I'm writing this one out. MP, AP, I'm perfectly willing to accept those abbreviations. We get how many such committees? First case, we had n times 2 to the n-1, and now to that I have to add n times n-1 times 2 to the n-2 such committees. Now the question is, does that somehow agree with the summation? So we have to do a little simplification here, right? This equals, let's see, what should I maybe do? How about factoring the 2 to the n-2, right? So I can take out the, I'll pull it out on the right side so that it's matching up with how I wrote the formula. So if I pull that out, then on the first term, I have an n. And then on the second term, I have, oh, wait a second. I meant to pull out, sorry, I meant to pull out 2 to the n-2. So in that case, I screwed this up too. Let's start over. Okay, I factored out 2 to the n-2. In the first term, I have an n and one of the 2's because there's an extra 2 here, so it's actually 2n, right? And then on the second term, I have n times the quantity n-1. I am hoping that now we could factor out an n from here, and that'll leave me with 2 plus n-1, which is actually n plus 1. So it actually does work out. So this is equal to n times n plus 1 times 2 to the n-2. And that is the end of that proof. Takes a little bit of work. I think the hardest part really is figuring out what it is you should be counting. And that was Fernando's idea, which is really good. A president and a secretary of a committee. And then we have to think about how we can count it in two different ways. I would not have figured it out by trying to come up with something that is counted by this. This is confusing. It's like, wait a minute, you only have n, do you have n people or do you have n plus one people? But if it's n plus one people, then why is this n minus two? It's not as clear. So in this case, I dug my teeth into the right-hand side, came up with something to count that really matches up with that cleanly, and then had to do a little bit of algebra to work out the other side. But see, the simplified algebra hides kind of where the cases came from in the first place. So I think this is kind of a good, slightly more intermediate level example of a combinatorial proof to think through. What do you guys think? Are there any questions? We've done a few of these here. Let's see. That mostly finishes up this whole chapter. I guess there's one little loose end I'm gonna do for 5 minutes, and then we're gonna spend the last part of the class. I'm gonna let you try a couple of these. But let me do one last thing here this will basically finish chapter 5 so that on Thursday we can start the next we can start clean with a new topic on Thursday. I want to just talk about and we have mentioned this already, the multinomial coefficients. Not just the binomial coefficients, but the multinomial coefficients. This is, those coefficients that showed up in the Mississippi problem where you have like a number on top of this expression and then several numbers underneath of it. Right, let me just take a quick minute and give you the theorem on this. This is actually in a separate section by itself in the book. So I'll do this briefly. This is just called the multinomial theorem. So I know we're totally changing topics here a little bit. This is not the same thing as what we've been practicing so far today. But this is the sort of result that will allow us to expand. So this allows us to expand expressions that are a little more generic, like say x1 plus x2 plus dot 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 plus x sub t to the n power. So we learned the binomial theorem, which was just x plus y to the n. What this is x1 plus x2 plus x3 plus x4 and so on to the n. Now, of course, you could expand this by just viewing it as iterative binomial theorems. Like you could take these t terms and kind of put them into two, add some parentheses, like you could just do that and say, well, this is x and this is y. And then just use your binomial theorem on that. So you can do that, but that's a tedious way of kind of proceeding. It's a little bit easier if we just kind of imagine what would happen if we multiplied this out and what the terms would look like, right? So a typical term of this expansion would be, let's try to write out how it would look like a typical term. It would have some x1s, let's say x1 to the n1, and then it would have some x2s, let's say x2 to the n2, all the way up to xt to the nt. So you'd have terms that look like that. And does anybody want to suggest what would be the constraints on those exponents? If I'm thinking about just a particular term of the expansion of this whole thing?
Yeah.
Gotcha.
Would they add up to n?
Yeah, they'd have to add up to n. Is that what you were gonna say? Yeah, absolutely, because you imagine you have n of these sitting side by side, and you're going to grab exactly one term from each factor. So that's a total of n terms. And so n1 plus n2 plus dot 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 up to n sub t needs to add up to whatever this fixed value of n turns out to be, right? Okay, so that's kind of the idea here. And how many of these terms would there be? Because that's gonna be the coefficient in front. Like, I'm gonna see this term many times. So just to scribble here for a second, if I had x plus y plus z to the 10th, right? You know, I'll have a bunch of terms added up over here, but one of the terms will be, you know, x to the 5th times y cubed times z squared. That's an example. And to get this term, I would have to have taken 5 x's, 3 y's, and 2 z's from these 10 factors. So I'm going to be choosing out of the 10 factors, I'm going to choose the x 5 times. And from the remaining 5 factors, I'm going to choose the y 3 of those times. And then from the remaining 2 factors, I would choose 2 z's, right? So it's actually kind of like stars and bars, isn't it? It's basically like, it's like a stars and bars problem. I mean, this is a fixed number right here. This is 10, for example. And I'm asking how many ways are there to add these exponents up to 10? I mean, we actually did stars and bars to solve those problems, didn't we? Where it said x1 plus x2 plus x3 adds up to 10. How many solutions are there? And we created whatever it was, t minus 1 bars. And we had n stars. And we just did stars and bars. So it was a very simple answer in terms of stars and bars. So essentially, let's actually write some of this down now. This is very quick. It's not anything too deep. How many of these terms are there? I'll ask the question and then I'm going to answer it right away. Right, so the answer, we just discussed it already. The answer is that it is the number of ways of solving that equation that I just wrote down, solving n1 plus n2 plus ... plus n sub t equals n. I want everybody to be clear, n is fixed. It's just like some specific number that's been fixed. Solving that for n1, n2, and so on up to nt, where each of those is greater than or equal to 0, right? So we have no other constraints than that. It's just the number of such solutions. And so this is, right? So this is actually going to be yeah, so, you know, you're going to, as I said a moment ago, let me just get my train of thought again. I have n of these factors. I'm going to choose, so I have n. I'm going to choose n1 of them to grab the x1 from. And then I'm going to choose n2 of those factors to grab the x2 from. And so on and so on and so on up to n sub t. It's this is the multinomial coefficient that I'm talking about. And of course, we looked at this earlier. This is like the Mississippi problem, right? So this is n factorial divided by n1 factorial times n2 factorial and ... all the way up to n sub t factorial. That's basically going to be the number of ways of doing that. And this is called right here. I think I might have written this down before, but just to be totally certain, this is the multinomial coefficient. It's not a binomial coefficient. And when there's more than 2 numbers on the bottom like that, then it's a multinomial coefficient instead. Right. So then now I can state the theorem, and then that will be it for this little section. So here's my theorem for this section. It just says let n be a fixed positive integer. So that's what we've been talking about here all along. So we take a fixed positive integer n. Then for all x1, comma, x2, comma, dot, 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 up to x sub t, we have. Here's the theorem. The expansion of x1 plus x2 plus dot, 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 plus xt, all raised to the power of n. This is going to be the summation of these multinomial coefficients. So I have n on top, and then I have n1, comma, n2, comma, dot, 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 comma, nt on the bottom, times x1 to the n1 times x2 to the n2, and dot, 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 times xt to the nt. Where, I have to explain this a little bit, the summation, you notice I'm not summing from something to something here, I'm just writing this kind of abstractly as a sum. The summation extends over all non-negative integer solutions. The summation extends over all non-negative integer solutions, n1, n2, and so on up to nt of this equation, n1 plus n2 plus dot, 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 plus n sub t equals n. That's it. That's the whole ball of wax. So, in other words, you're going to put every possible combination of, so the number on top is fixed, right? The n on top is fixed, let's say it's 10. So this might be 10. So what's going on the bottom then is all possible ways to have t numbers adding up to 10, right? And where we do care about the order, because, if I have, if n1 is 5 and n2 is 3, that's different than n1 being 3 and n2 being 5, right? Because it's a different term, a different series of powers of x's here. So it does make a difference in that sense. So yeah, that's the whole theorem essentially. The proof is sort of, you don't have to write it down, because basically what is the proof? The proof is, well, imagine expanding this out. Okay, every single term will consist of things that look like this, right? Where these add up to n. And how many of this particular term do we get? Well, it's exactly this, because that's what I explained over there, the number of ways of solving this equation, which is just this multinomial coefficient. So the proof is actually sort of in the explanation that led up to the statement of the theorem. I don't really need to write anything more than that. Yeah, but it's a nice generalization of the binomial theorem that we did last week. So, questions on that? Comments? Complaints? Issues? Heath? A little example for it. Let me see if I can think of one. You guys don't mind if we do the group work on Thursday? Okay, great. We only got a couple minutes, so I'll just try to explain it briefly. I did fix the clock finally. I stood up on the chair and it swiveled around and I almost went tumbling to the ground. So just a quick example of this. Like n equals 10. I hope it's not gonna be too big. Actually, you know what? Let's do n equals 5. I know you guys I already said I'm hungry, and you guys brought up apples, oranges, bananas, and now I'm really.
But then you said your wrist hurt, so
I don't want to write as much, so I'm gonna make smaller numbers. Okay, so this is, obviously this is x plus y plus z 5 times. I'm gonna actually write it out 5 times since my wrist hurts. I just like to visualize it, at least the first time I'm trying to understand something. So I imagine writing it out 5 times like that. And it's just the idea of foiling it out. When you foil this out, every single term, so you'll grab one of these, one of these, one of these, one of these, and one of these, right? You'll grab one of each of the terms of each factor. And what you'll have is an expression that looks like some x's times some y's times some z's, right? So you'll get a bunch of terms added together with x to a power, I'll call it n1, y to a power, which I'll call n2, and z to a power, which I'll call n3. And now what we're looking at is all possible ways for n1, n2, and n3 to add up to 5. And you can ask yourself, well, how many of those could you have? Well, you know, these are with non-negative integers. The answer is that you're going to put, you know, your n value of 5 here, and now you're going to be choosing, you know, whatever n1, n2, and n3 are. And what are the choices? Can we write them all down? We could have 5, 0, and 0. Right? I won't write them all down. I can tell already. I'm not going to be doing that. I'll write down some of them though. We could have 4, 1, and 0. We could have 3, 2, and 0, or we could have 3, 1, and 1, and so on and so on. But actually, so there's no rule that says n1 has to be bigger than n2 and bigger than n3. So we would have to shuffle these into every possible order as well. But these are the kind of terms that you're creating when you do this, right? So, for example, I'll just go dot, dot, dot like that. Is that okay? And then what I'm going to do is actually write out the first couple of terms. So the first term we have n1 is 5, n2 is 0, and n3 is 0. Well, that's just 5, choose 5, 0, 0 of x to the 5th, right? And y to the 0 and z to the 0. And then the next term would be 5, choose 4, 1, 0 times x to the 4th times y. And remember, this number is actually equal to 5. 5 factorial divided by 4 factorial and 1 factorial. And that makes sense that it would be 5 because I have 5 different ways of grabbing 4 x's and 1 y from the 5 factors, right? I can either grab the y from here, or from here, or from here, or from here, or from here. So that makes sense that it's 5 ways. The next term would be 5, choose 3, 2, 0. And this one would just look like x cubed y squared. That's another term in this big expansion. And again, you know, what is this really? This is, you know, I have 5 slots and I'm going to choose 3 of them to put the x's in. 5, choose 3 ways to do that. And then I have 2 slots left. I specifically choose to put those y's there instead of, and I don't use the z's at all. Kind of following this? Okay, and then it just keeps going. I picked a number that's too big already, but you sort of see the idea?
Yeah.
Okay, it goes on for a long time. I mean, the number of terms is, actually the number of terms here is the number of solutions you have to this, and that's where the stars and bars. 5 stars, 2 bars. So there would be what, 7 choose 2, which is 21 terms. Right, so I've written down 4 of them here, right? 3 of them here, but there's a 4th one that we could write down, 5, 3, 1, 1. Obviously that's x cubed y z. So I wrote down the first 4 of them, but there's really 21 of them. If I write them all down, this would be a very, very big expansion that we would end up with. So, does that help a little bit? Okay. Guys, we'll just do the group work on Thursday at the start of class. I think that'll be fine. You can always peek at it ahead of time if it would be helpful, but hopefully the combinatorial proofs we did today will also help you with the homework. I'm hoping it will anyway. So I'm going to go downstairs if anybody wants to chat. Litzy and no, Kevin's not here today. Litzy, got your quiz for you. And you guys are free to go. I will see you on Thursday at 9:00. Have a great day, everybody. Bye-bye. Hey, Julie.
Because of the wording.
Like, could I not send him any pictures?
It's not just the wording. What the problem is that you're presupposing a scenario where the tickets were all spread out where I got one ticket in each box. So you're, what if I didn't get any tickets for the first 3 weeks of the semester?
Two different things I should have just said, because if I can't have more than 3 in one box.
That we know. Yes, that's true. The issue here is that you're creating a contradiction by assuming how the scenario is going to go.
Yes.
Yeah, and that assumption in this case